of the heat part also, heat and everything?
Heat, but I'll discuss the questions, but I'll not be keeping a test on that.
No, so I mean, in the last when we will be conducting the full syllabus test, would it consist of all the problems like oscillation waves,
It will.
everything?
It, let me see. If possible, I'll not give that. Okay, if possible, I'll give that. That's not a big deal. As per the projection, I will give you what I have projected during before the beginning of or commencement of our course. Before the projection, whatever I have given, I'll try to give that only. Okay, if you feel that not necessary, let us see, or maybe we can discuss only that particular part, which only those topics which we have discussed. I hope the board is visible to all of you, right? Yes or no? So in between today is a maybe 2.5 hour to 3 hour session, and in between, just a second. Audible, visible, right? Let us quickly complete the questions, guys. Okay. So till here we have discussed. If the radius of the first orbit of hydrogen atom is 5.29 into 10 power minus 11 meters, and the radius of the third orbit will be how much they are asking. So how will radius vary, beta? Radius of nth orbit, it will vary as n square by z times of r naught, because they have mentioned hydrogen atom. So and they're asking radius in third orbit. It will be 3 square divided by hydrogen atom will be 1. R naught value in the first case it is given as 5.29 into 10 power minus 11. So 9 into 5, 45 you will get, to which will be near about 47.61 into 10 power minus 11 meters. Okay. So R value will vary as n square by z into R naught. 47.61 will be your answer in this case. Then energy of hydrogen atom in its ground state is minus 13.6 electrovolt. The ionization energy of electron from first excited state. See, what is the meaning of ionization energy? It means I need to remove the electron from that particular orbit and I need to send it to somewhere to infinity. So, what is the energy in ground state? It is given as minus 13.6. So, here energy in the ground state, or which is the first state, will be minus 13.6 electrovolt. Ionization energy of electron from first excited state. First excited state means will it be second state or not? In second state, what is the energy? It is minus 3.4 electrovolt. Yes or no? So electron which is revolving in second state has this much of energy. I want to remove that electron. If I want to remove the electron, you need to make the energy of electron zero. So when can you make the energy of electron zero? If you supply plus 3.4 electrovolt. Yes or no? So here the ionization energy of electron in first excited state of hydrogen atom will be 3.4 electrovolt. If it is in ground state or first state, you should give. See, if you want to remove the electron, again, how do you ionize an atom? If you remove an electron, guys, doubly ionized, two electrons you are removing. So singly ionized, if you consider, what will happen? One electron you have to remove. If it is in ground state, then you need to give minus 13.6 electrovolt of energy. And always remember the ionization potential. If they ask you ionization potential, then for hydrogen atom, if you take for hydrogen like atoms, it will be 13.6 into z square. In which orbit is it? It is first orbit. So whenever you want to ionization energy only, if I write, so ionization energy will be 13.6 z square in electrovolt, right? Or I can write for hydrogen for Bohr atom in nth orbit. If I consider, it will be 13.6 z square by n square electrovolt. It is in nth orbit. Okay, this thing you should remember. In order to ionize, I need to make the energy of the electron zero. So energy of electron which is in second state of hydrogen atom is minus 3.4. In order to make it zero, I have to just give plus 3.4. Clear, everyone? Let us talk about the next question. They're asking us to find out what is the ratio of angular speed to the tangential speed of electron in nth orbit. So angular speed, we know it is given as omega. Tangential speed, you can take it as v. right? So how we can write omega value as, again, always remember, electron revolves around the nucleus in circular path, performing or executing uniform circular motion, right? So what is omega value? I can write it as V by R. Yes or no? Or this entire value, if you see, it will become 1 by R. So the ratio of angular speed to the tangential speed in nth orbit, they are saying. How is radius varying? Radius is varying as directly proportional to R square. So 1 by R will be, it will be proportional to n power minus 2. Or I can write 1 by R will be proportional to n square. So omega by R value is basically given as 1 by R, right? So it will be inversely proportional to n square, should be the answer. I hope it is clear, all of you. Let us talk about the next question. Hydrogen atom from excited states comes to ground state by emitting a photon of wavelength lambda. If R is the Rydberg's constant, the principal quantum number n of the excited state, they are saying. So from some excited state, it is coming to which state, beta? Ground state. So what I can write? En minus E naught. Yes or no? Or you can better write it as, from excited state, it is coming to ground state. So what is the energy of the photon emitted or absorbed, guys? The energy of the photon emitted or absorbed will be change in the energies of the different energy levels again. So finally, it is coming from some excited state. It is coming to where, beta? Ground state. So I can write, if I want to write En minus E naught here. So En minus E naught. This is difference in the energy levels. So this will be nothing but the energy of the photon or energy of the, you can consider gamma rays. So energy in nth state minus E naught. If lambda is the wavelength given, then I can write energy of photon as hc by lambda. What is energy in nth state for hydrogen atom, beta? I can write it as E naught divided by how much here? E naught divided by n square, you can write. Minus of E naught will be equal to hc divided by lambda. Achha, I think they're not considering this fact again. We can use wavelength again, guys. Wavelength of photon formula, as I have told you yesterday, right? While you are doing some question related to fund series. So I can use 1 by lambda. Wave number value will be R into which state it is making a transition? Into ground state. So here you will get 1 square minus 1 by, from which state? From n square. You can write as into z square, which is anyhow. So what I can write, 1 by lambda value will be R into 1 minus 1 by n square. Yes or no? So I can also write 1 by lambda R value will be 1 minus 1 by n square. So 1 by n square value, we can take it as 1 minus 1 by lambda R, which turns out to be lambda R minus 1 divided by lambda R. So n square value, I can write it as lambda R divided by lambda R minus 1. So n value will be square root of lambda R divided by lambda R minus 1. Clear, everyone? Understood. Hydrogen atom from an excited state comes to a ground state, they have said, by emitting a photon. So always remember, we have Rydberg's formula again. The wave number, if you see, it will be given as 1 by lambda, which is R into 1 by, what is this here, n value? It is the principal quantum number of that orbit into which it is making a transition. Here n value will be principal quantum number of that orbit from which it is making a transition. Okay, again, it's a good question. Lambda r, under root of lambda r divided by lambda r minus 1. Second option should be the answer for that. Clear, everyone? Understood, all of you? Let's see the next case, guys. The element which has K alpha X-ray line of wavelength 1.8 angstrom is what they are asking. Okay, so what we can use again, I've told you yesterday, Moseley's law, right? What is Moseley's law stating again? So basically, it is giving the relation between the frequency as well as the atomic number. So how I can write this as a into z minus b, we can write. What will I get? New value as a square into z minus b whole square, right? So for K alpha X-ray, these are characteristic X-rays, guys. So when will K alpha X-ray be formed? When the transition is made from L shell to K shell, then K alpha X-ray will be formed again. So for K alpha X-ray, A value will be given as root over 3RC by 4, and B value will be given as 1. So what I can write frequency as? I can write as A square value will be anyhow 3RC by 4 into Z minus 1 whole square. So how can I write the value of frequency as? Frequency can be written as C by lambda again. C by lambda value will be 3RC by 4 into Z minus 1 whole square. So from this we can cancel out C and C beta. So what are we going to get Z minus 1 whole square as? Z minus 1 whole square, I'll get it as 4 divided by 3 lambda into R. So what is 1 by R? 1 by R happens to be 912 angstrom, guys. So I can write it as 4 by 3. 1 by R will be 912 angstrom, although it is given some value. You can take it as by 1.8. So Z minus 1 whole square if I take, guys. Direct questions you will get based on this again. So Z minus 1 whole square if we consider, you will get it as how much? So if I write 4 into 912 divided by 5.4, you will get, guys. So if I take this as 1000 and this as 5, 2000 you will be getting. Or if you just solve for it, guys, you will get it as 40 divided by 54 into 912. Okay. So if you solve for this, you will get the value of Z minus 1. So can you find that value, all of you? Yes or no? So near about, you can just check it how much you are going to get. If you take this as 50, you will get it as near about 18 again. Okay. So almost 18 you are going to get. 18 into 4 will be 3200 again. The square root of 3200, maybe near about 25 or something like that you are going to get, guys. So 25, 27 maybe. So you can solve for that. So Z minus 1 whole square, you will get some value. From that Z value will be that value plus 1. Okay. Or you can say Z minus whole square will get some value. Z value you can take, or you can write one more step you can add here. How much is 675? Root 675? 25, no it is? So Z minus whole square, you will get it as 675, guys. So I'll get Z minus 1 as 25, implies Z value will be 26. So you will get the answer as iron, whose Z value will be 26 again. K alpha characteristic X-ray will be formed when transition of electron will take place from L shell to a vacancy created in K shell again. Okay.
So it should be 625, so 25.
675 आया ना?
So
26. 676 is 26, no? 26. You'll get 27 then.
So how did you got the A value as under root of 3RC by 4?
It is specific for K alpha X-ray.
Okay.
Next question, if you see angular momentum of an electron in hydrogen atom is, so we all know angular momentum will be integral multiple of h by 2 pi. So it is given as 4h by 2 pi. So implies what we can write here, n value will be 4. Yes or no? And we know in fourth orbit implies what is the energy in fourth orbit? First orbit minus 13.6 minus 3.4 minus 1.51, I think minus 0.85 you will get. Minus 0.5 is the energy in fourth orbit. Negative energy means it is a bounded orbit again, or the electron we can consider it is bound to rotate or bound to revolve in your circular orbit. So we know kinetic energy will be given as minus of total energy again. In any bounded system, kinetic energy will be minus of total energy, or total energy will be minus of kinetic energy. So what will be the kinetic energy of the electron in that particular case? You are going to get it as 0.85 electrovolt. Clear, all of you? I hope it is clear. Especially if you see, if a photon energy is near about 3.5 electrovolt, then it causes the sunburn, that is to break the bond in molecules of the human skin. This wavelength corresponds to what they are asking. There is something called as electromagnetic spectrum, guys. So what we can write now, whenever energy is given, how can I write wavelength again? I can write it as hc divided by energy. Energy should be taken in electrovolt. I'll get the answer in angstrom, guys. So what is the wavelength here? hc can be written as, directly I can write 12,400 beta. So I can write it as 12,400 divided by energy is taken in electrovolt again. So I can write 12,400 divided by 3.5. So how much will this be? 124 by 3.5 if I take 35. How much are, guys? What did I do? You'll get it as 3542 angstrom. 3542.86 angstrom. Whatever you're getting. So this wavelength will correspond to how much they are asking. So I can write this as, this can be taken as 3.5 into 10 power minus 10, it is 10 power minus 7 meters you will get. Right. So if you see the range again, first we have gamma rays. Gamma rays will be from 10 power minus 14 to 10 power minus 10. Then we have X-rays. X-rays will be from 10 power minus 12 to 10 power minus 8. Okay. Then we have your UV rays. UV rays will be from 10 power minus 10 to 10 power minus 7 again, 3.8 into 10 power minus 7. Okay. So this value will lie in UV region again, if I am not wrong. Okay. It will lie in UV region. Spectrum, you remember, guys? Gamma rays, X-rays, UV, visible, infrared, micro, radio. This you should remember. But we'll study electromagnetic waves also. If the radius of shortest orbit in a single electron system is 18 picometer, right? It may be shortest orbit they are saying. Radius is given as how much? 18 picometer. Pico means 10 power minus 12 meters, guys. Right? So it is going to be which single electron system? Again, always remember Bohr's model is valid only for a single electron system. 2019 question of NEET, guys. That very important case. So here they have given radius as 18 into 10 power minus 12 meter. Shortest orbit will be nothing but your first orbit. So what is radius variation again? We can write it as n square divided by z into r naught. So what did we get radius here? 18 into 10 power minus 12 we got. Anyhow, it will be in first case only. Z into what is R naught value? 0.53 angstrom we will write, guys. So I can take it as 53. Yes or no? 53 into 0.529 you will get. So I can take it as 53 into 10 power minus 12. Okay. So Z value, how much will you get? This will be 53 divided by 18 because 10 power minus 12 and 10 power minus 12 will get cancelled out. So 18 threes usually happens to be 54, guys. So it's approximately 3 again, which will be Li plus 2. Clear, all of you? Next case. Simple Bohr model cannot be directly applied to calculate the energy levels of an electron with many electrons because, right? So in this situation, simple Bohr model cannot be directly applied to calculate the energy level of an atom with many electrons. It is applicable to only single electron system, guys. So why we cannot apply? The electrons collide with each other, electrons not being subjected to a central force. This is wrong. The force between the nucleus and an electron will no longer be given by Coulomb's law. This is also wrong, right? So out of these two, it should be, guys. Simple Bohr model cannot be directly applied to calculate the energy levels of an atom with many electrons. This is because of which case? I think it should be screening effect. However, I'll just cross check it once again, guys. Next question. If you see, if wavelength of the first line of Balmer series of hydrogen is lambda, wavelength of second line of this series. Now, I have told you how we obtain shortest wavelength and longest wavelength. Shortest wavelength is obtained from where to where? From infinity to given state. Yes or no? So here in this situation, what they have given, for, let us talk about wavelength of Balmer series again. For hydrogen atom, if I take, it will be given as R into, the transition will be made into second state, guys. So you'll get it as 1 by 2 square minus 1 by from n square into z square. Here what will n value be? N value will be more than 2, 3, 4, 5, 6, so on. By emission spectra I am saying. So if n value is less than 2, only one possibility is there, which is 1. So if n value is 1, then it will be absorption spectra, guys. So here 1 by lambda value will be R into 1 by 2 square minus 1 by n square. Longest wavelength, when will you obtain? When transition is made from infinity to given state. Shortest wavelength you will obtain when transition is made from infinity to given state. Longest wavelength is obtained when transition is made from just the above state to the given state. So here first line of Balmer series, when I talk about first line of Balmer series, when I say first line of Balmer series, the transition should be made from 3 to 2, guys. Then if we talk about second line of Balmer series, then the transition should be made from 4 to 2, guys. So in this case, what will I get? 1 by lambda value will be R into 1 by 2 square minus 1 by 3 square into, anyhow for hydrogen atom they have given, so you can take it as 1 square. So what will I get this as? R into 1 by 4 minus 1 by 9, 5 by 36 I believe. So you'll get as 5R divided by 36 here. Here in the same manner, 1 by lambda dash if I take, you'll get it as R into 1 by 2 square minus 1 by 4 square into, again 1 square only you will get. 16 you will get, 4 minus 1, 3 you will have here, guys. So I'll get it as 3R divided by 16 I believe, if I'm not wrong. Yes or no, guys? 1 by 4 minus 1 by 16 you will get. 4 minus 1 divided by 16. 3R by 16 you are going to get. Now what I'll do, I'll divide both of them, guys. What are we going to get? 1 by lambda whole divided by 1 by lambda dash. So if I divide both of them, I'll get lambda dash divided by lambda. This is 5R divided by 36 whole divided by 3R divided by 16. So from this I'll get, what you can do is, so I can write simply 5 into 16 divided by 3 into 36. So if you take 4 table again, right, 4 fours you are going to get 4 nines. 20 divided by 27 you are going to get. So it will be 20 divided by 27. So what will I get lambda dash value as? 20 divided by 27 into lambda will be our de Broglie wavelength. Clear, everyone? First line will always be from just the above state to the given state. Second line will be again 2 states above to the given state. Clear, all of you? Yes or no, everyone? Direct formulas, guys. Again, you don't have any difficulty in solving such type of question. Atoms, so you can do easily. Next thing, let us see. The diagram shows energy levels for an electron in a certain atom. Which transition shown represents the emission of photon with maximum energy? First one, you see, it is making a transition from lower energy level to higher energy level. This is your absorption spectra, but they have asked us to find emission spectra, guys. So which will have maximum energy? So if you write, this is minus 13.6 electrovolt, this is minus 3.4 electrovolt, this is minus 1.51 electrovolt, this is 0.85 electrovolt. Now if you see the transition between these two, right, fourth case if I observe, so how much will be the energy here? 10.2 electrovolt. In the same manner, if I see the transition between fourth and second, what will be the difference again? I'll get it as near about 2. I think 2.45, maybe. No, I think 2.55 you will get. Yes or no? So if you just look at it, you will get it as 2.55 electrovolt again. 0.85 if you do, I think you'll get correct only. Clear, 2.55. And if you take this situation between these two, then I'm going to get how much, beta? I think 0.65 you will get. 0.65 or 0.66 electrovolt you will take. So in which transition will energy emitted be more? When the transition is made from, out of the given transitions, when the transition is made from second state to first state. Okay, so which will be fourth case. Now most of you will write first case as the answer because their energy difference will be more. So if you look at the energy difference between first and second, first and last here, so what will I get here? I think you will get it as near about 12.75, I guess. You will get 12.75 electrovolt. So in which case energy is maximum, energy of photon is maximum, energy of photon is maximum in first case, but that is related to absorption spectra. They are saying emission of photon. The emission of photon will take place in second, third, and fourth. Maximum energy will take place in fourth case. Clear, all of you? Yes or no? So already we have done this question. We got it as lambda r divided by lambda r minus 1. Okay, we already done the question, guys. Let us see the next case. Frequencies are given. If nu1 is the frequency of series limit of Lyman, right? Nu2 is the frequency of first line of Lyman series, and Nu3 is the frequency of the series limit of Balmer series again. Okay, what are they asking? They're asking relation again. Nu1 is the frequency of series limit of Lyman series, guys. Lyman series means it will vary from where to where. You can take from any state to ground state. Yes or no? Nu2 is the frequency of first line of Lyman series. First line of Lyman series, see, this is Nu1 means it is making a transition from infinity to 1. Nu2 means it is making a transition from 2 to 1. Right? Nu3 will be when it is making a transition from where to where, beta? Infinity to 2. Okay. Now here transition is made from infinity to 1, guys. So what we can write? Energy will be emitted. What we can write? E infinity minus E1 will be equal to h nu1. Difference in the energy will be nothing but energy of the photon. Here in this case, E2 minus E1, what are we going to get? H nu2. Now in this situation, what I'll get? E infinity minus E2. I'm going to get it as what, beta? H nu3. Three equations we have. What I'll do, I'll take these two equations. Okay, and I'll subtract both of them. I'll take these two equations, beta, which is E infinity minus E1 will be equal to H nu1, and we have E infinity minus E2 will be equal to H nu3. So I'll subtract both of the equations. If I subtract both of the equations, E infinity minus infinity will get cancelled. So what I'll be left out with, beta, here? I'm going to be left out with E2 minus E1 will be equal to H nu1 minus H nu3. So I can write E2 minus E1 as H into nu1 minus nu3. But we already got E2 minus E1 as H nu2. So H nu2 value will be H into nu1 minus nu3. So from this we can add up, right? We can say that H and H will get cancelled out. What will nu2 value be, beta? It will be nu1 difference nu3 or nu1 minus nu3. Clear? We don't have any option here. Just check. Did we do any mistake? Nu2 value should be nu1 minus nu3. So it's already there. No, first option will be the answer. Clear, everyone? So here you may get uh, again. Basically, we should write energy of final state minus energy of initial state. If I write energy of final state minus energy of initial state, you will get minus sign. So what will that minus indicate? It indicates that energy is emitted again. Okay. Understood? Yes or no? Lyman series will lie anywhere when transition is made from any state to first state. First line of Lyman series will be just the above state to the given state again. So second state to first state. Right? Similarly, Balmer series will lie from any state to second state. Okay. That clear? In Bohr's model of the hydrogen atom, the lowest orbit corresponds to what, guys? The lowest orbit will always correspond to minimum energy. Minus 13.6 is the minimum energy. Choose the incorrect statement, it seems. Lyman series lies in UV region. Always remember very simple logic, guys. They will ask you Lyman, Balmer, passion. In physics, we have these three only. Okay, fund and bracket and fund, they will not ask. So Lyman will lie in which region, beta? UV. Balmer will be lying in visible. Passion will lie in IR. Select the incorrect statement they are saying. Lyman series lies in UV region, it is correct statement. Balmer series lies partly in visible region. Yes, it is also correct statement. Fund series will lie in far infrared region. Yes, it is also correct statement. Passion series lies in UV region is wrong statement. It will lie in near infrared again. Okay, Lyman, Balmer, Passion. So which is incorrect statement here? Passion series lies in UV region will be wrong. You just remember Lyman, Balmer, Passion, Lyman UV, Balmer visible, Passion infrared, guys. Okay, and bracket fund will also lie in infrared only. Understood, all of you? I hope you have understood it. Why always this question has been asked? Okay, you have done this. You can remove it. When hydrogen atom is raised from ground state to fifth state, guys, what is happening? They are saying when it is raised from where to where? Ground state to fifth state. So let us talk about So energy will be changing from where? Minus 13.6 electrovolt to how much? Fifth state will be, I think you will get it as minus 0.54 electrovolt. Because minus 13.6 minus 3.4 minus 1.51 minus 0.85 minus 0.54 you can take. So this is the situation. Energy is changing. So energy is becoming less negative. So total energy value is increasing, guys. This is related to what? Energy. If we talk about kinetic energy, will it be negative of total energy or not? So kinetic energy will vary from 13.6 electrovolt to 0.54 electrovolt. What has happened to kinetic energy? Kinetic energy is decreasing. Total energy is increasing. What will happen to total energy now? Basically, total energy will be given as two times the potential energy will be given as two times the total energy now. Total energy here it is, so I'll get it as minus 27.2 electrovolt. Then it will become somewhere around 1.08. You can write minus 1.08 electrovolt. So what is happening to potential energy, beta? If you look at potential energy also, right, it is changing from more negative value to less negative value. So obviously this will also increase. So whenever it is taken from ground state to fifth state, kinetic energy will decrease and potential energy will be increasing, guys. So fourth option should be the answer for this. Understood, all of you? Always remember, in any bounded system you may take planet revolving around the sun, right? Satellite revolving around the earth, electron revolving around the nucleus. These are all bounded systems. For bounded system, total energy value will always be negative, guys. And what will be total energy? It will be minus of kinetic energy. What will be potential energy? It will be again minus of two times the kinetic energy. So if they ask you to find ratio of kinetic to potential to total, if they ask you, guys, kinetic to potential to total, kinetic energy you can write it as k only, potential is minus 2k, total is minus k. So I'll get it as 1 is to minus 2 is to minus 1, or I can write minus 1 is to 2 is to 1. This will be true for all the bounded systems, guys. Whether you take a planet sun system, whether you take a satellite earth system, whether you take an electron nucleus. So this ratio will always remain constant. Kinetic energy to total potential energy to total energy will always be minus 1 is to 2 is to 1. So whenever it is taken, whenever hydrogen atom is taken from ground state to fifth state, what will happen? Total energy value will be increasing, kinetic energy will be decreasing, potential energy will be increasing. Clear, all of you? Next case, if you see, choose the incorrect option for Bohr's model of the hydrogen atom. Radius of nth orbit is proportional to n square. Yes, it is correct. Angular momentum of electron in orbit is an integral multiple of h by 2 pi. Yes, it is correct. The magnitude of potential energy of a electron in any orbit is greater than its kinetic energy. Yes, it is also correct. Total energy of an electron in nth orbit is proportional to n. No, it is inversely proportional to n square, guys. So this would be our incorrect statement. Okay, yes or no? Let's see next question. In an X-ray tube, heat is produced at the rate of 200 watt. So power is given to us. If X-ray tube is operated at 20 kilovolt, then current in the circuit they are asking. Assume that only small fraction of kinetic energy of electron is converted into X-rays. So what we can write here, power can be written as V into I beta. So 200 value will be 20 into 10 cube into I. So what will I get here? Obviously, 20 ones, 20 tens you will get. So what will I value be beta? 10 into 10 power minus 3 you can write, which turns out to be 10 milliampere. Power will always be written as V into I, guys. Potential difference into current. The energy of an electron in an excited hydrogen atom is minus 3.4 electrovolt. So in which state it is? Minus 3.4 means here n value is how much beta? Here n value will be 2. It is in second state or first excited state. Angular momentum of the electron in this state. What is angular momentum? Again, we know it is nh divided by 2 pi. So we can write it as 2h divided by 2 pi, which turns out to be h by pi, which is 6.6 into 10 power minus 34 divided by 3.14 you can take, which will be 2.1 into 10 power minus 34 joule second, guys. Clear, everyone? Angular momentum, again, two things only we have in Bohr's modulus, guys. whenever, again, he stated that electrons revolve around the nucleus in circular path. So whenever any object is performing circular motion, there should be a certain force directed towards the center called as centripetal force. So in case of electron revolving around the nucleus, who will be providing the necessary centripetal force? The electrostatic force of attraction between the nucleus and the electron. So I'll write E into ZE divided by 4 pi epsilon naught r square will be centripetal force. And he also said that we have to use the quantum concept for explaining the stability of the atom. So he said angular momentum of the electron about the nucleus will be integral multiple of h divided by 2 pi. Understood, all of you? Let us see. Ionization energy of a hydrogen like Bohr atom is 4 Rydbergs, it seems. Wavelength of radiation emitted when the electron jumps from first excited state to the ground state is nearly how much they are asking. Okay. So 1 Rydberg is given as RHC, guys. So they are asking what is the wavelength of the radiation. What we can write, 1 by lambda value, we can write it as R into 1 by, it is making a transition from where? From first excited state to ground state, guys. So I'll get 1 by 1 square minus 1 by 2 square. Hydrogen like atom is given. Ionization energy of hydrogen like atom is 4 Rydberg. So just now I've told you what is ionization energy. It is basically given as 13.6 into Z square divided by N square. So ionization energy of a hydrogen like Bohr atom is 4 Rydberg, means it is considered to be ionization energy. Let us take in first state, guys. So what I'll get here? So ionization energy in first state, if I take, I'll get it as 13.6 into Z square, guys. So this is mentioned as 4 Rydberg, which is 13.6 into Z square. So I'll get Z square value here. 1 Rydberg is RHC. So 4 Rydberg, what I can write? This will become 4 into R into H into C. So 4 RHC divided by 13.6. Okay. Now they are asking us to find wavelength of the radiation emitted, guys. So I can write it as R into 1 by 1 square. Again, this can be taken as 1 minus 1 by 4. 1 minus 1 by 4 will be 3 by 4. But hydrogen like atom is given, so I can write Z square, guys. And how much did we get Z square value as? 4RHC divided by how much did we get? 13.6. I think I wrote something wrong here. Z square value will be correct only, guys. It is 4 Rydberg given. 1 Rydberg is given as RHC. So I can take it something like this. So what can be cancelled out? 4 and 4 will get cancelled out. So how much will be the value? Can you find it out, guys? Lambda value will be 13.2. Again, it is given in energy 13.6, no? 13.6 energy should be given in electrovolt here, guys. 13.6 electrovolt it is. So what I'll do, I'll convert into joules again. So how I can convert 1.6 into 10 power minus 19 divided by what are we going to get? 3 we have. R value, it can be written as, answer also is not given in Rydbergs again. So R value, how much is it, guys? R square we'll get, no? So whatever it is, I think you can solve for it. 3R square HC you will get. Okay. If you solve for it, you will get it something in this manner. Lambda value, if I take, it is 13.6 divided by 3 into 1.6 into 10 power minus 19 divided by H value is 6.6 into 10 power minus 34 into C value is 3 into 10 power 8. And R 1 by R value is 912 angstrom, guys. So I can write it as 912 into 912 angstrom square you will get. So I'll write it as 10 power minus 20 I will get again in this situation. Okay. So what will this turn out to be? Here you have 6.6 once. I can take it as approximately 2 times, guys. Then what are we going to get? To take the lambda value, here you can take these two as 900 and 900, guys. Minus 39 you will get into 10 power 4 you will get, which will be minus 35. So 9 nines 81 into 1.6 into 2 also we have. So 81 into 3.2 I will write directly. 81 into 3.2, in denominator you have 9. In numerator I got, here I took it as 900 and 900. So 10 power 4 we will get. 10 power minus 16, and in numerator we have 10 power minus 35 guys. And in denominator what will you have? In denominator I will have 10 power minus 26. Yes or no? So what we can take? 9 ones again. 9 nines approximately you can write, which is more than 9 again. I'm just writing it as 9 guys. So 9 into 3 will be 27 or not. So it will be more than 27. So this value will turn out to be how much? 18, 27.8 into, if you send this 10 power minus, how much will you get? 11 you will get. Sorry, 10 power minus 9 you will get. So if I just multiply and divide by 10, you will get it as 278 into 10 power minus 10 meters. It will be approximately 278 angstrom. Because I took 912 as 900, so it will be more than 278 guys. That will be close to 303 angstrom. Understood all of you? From the ionization energy, we have tried to calculate z square value. It's a good question again. Then by using Rydberg's formula, 1 by lambda is r into 1 minus 1 by n1 square minus 1 by n2 square into z square. From there, we were able to calculate the wavelength of the light which was emitted. Clear all of you? Yes or no? Let's see the next case. The ratio of, they're asking us to find out the ratio of wavelengths of first line of Lyman series and first line of Paschen series. So Lyman series first line, if I take Lyman series first line, it will be R into, transition should be made from where to where beta? From second state to first state. Hydrogen atom only I am taking. 1 by Paschen series, if I consider, the transition should be made from any state or just from the next state, fourth state to third state. This is for short first line again. First line will always be obtained in any series when the transition is made from just the above state to the given state, guys. So what I'll get, 1 minus 1 by 4 I'll get, which is 3 by 4. This you got it as 3r divided by 4. However, if I take this guy, 16 minus 9, you will get it as 7. 7r divided by 16 nines, I think you'll get it as 144. This you will get, guys. So if I divide 1 by lambda p whole divided by 1 by lambda l, I'll get it as 7r divided by 144 whole divided by 3r divided by 4, guys. What we can cancel out from this? You can cancel out r and r. And what are we going to be left out with? 4 ones we can take. 4, 3, 24 will be how much again? 4, 6, 24 I'm going to get, guys. Right? So what will this value be? Lambda L divided by lambda P, if I take, I'll get it as 7 divided by 36, 3, you are going to get it as 108. Okay. So this would be the ratio of first line of Lyman series to first line of Paschen series. Understood everyone? Yes or no? Has come from the below questions. Bohr's model for the spectra of hydrogen atom will be applicable to hydrogen in molecular form? No. Will not be applicable as it is for a helium atom. Then is valid at room temperatures only, predicts continuous as well as discrete spectral lines. What will it be? Will it be applicable to hydrogen in molecular form, guys? No, it is applicable for a single electron system. Ionic form you can consider. Will not be applicable as it is for a helium atom? Yes, for single electron system only. Is valid only at room temperatures? Not necessary, guys. It is valid at any temperature. It predicts continuous as well as discrete spectral lines. Although I'll just cross check this question. Next case, if you see, the electron is present in the minus 1.51 electrovolt. So here, what is n value beta? Will it be 3 or not? Third state. They're asking radius of the orbit in this radius of the electron in this orbit. Radius in nth state will be n square divided by z into r naught, guys. So what is n square divided by z into r naught here? N value will be 3 square divided by z is anyhow 1.53 angstrom you will have, which is 9 into 0.53 angstrom or 0.529 angstrom, which I'll get it as 4.77 angstrom. So whenever energy is given as minus 1.51, the electron will belong to third orbit, guys. Right, from there in third orbit, what will the radius be? N square by z into r naught. R naught value is 0.529 angstrom, or you can take it as 0.53 angstrom also, guys. Clear, everyone? Understood, all of you? Then what they are asking here in this question, the difference between n plus 1 Bohr radius and nth Bohr's radius is equal to n minus 1 Bohr's radius. Then what is the value of n they are asking? Again, very good question. We will just see it below here, guys. What they are saying, difference in n plus 1 minus nth orbit is equal to radius of n minus 1th orbit. Okay. Now, what is radius in nth orbit? How will it vary, beta? For hydrogen atom only if I take, or Bohr's radius is given, so you can take z also. So can I write it as n plus 1 whole square divided by z into r naught minus, here I'll get n square by z into r naught will be equal to, here what I'll write, n minus 1 whole square divided by z into r naught. What we can cancel out, beta? You can cancel out r naught, r naught, r naught, z, z, z. What will be left out with? N plus 1 square minus n square will be equal to n minus 1 whole square, guys. So what will this turn out to be? It is in the form a square minus b square or not here? A square minus b square means I can write a plus b, which I'll get it as 2n plus 1, and a minus b, which I'll get it as 1, should be equal to, it is in the form a minus b whole square, so I can write it as a square plus b square minus 2ab. Okay. So what will this turn out to be, guys? I'm going to get it as, it is a plus b into a minus b. If you do, these two will get cancelled, n and n will get cancelled. So 2n plus 1 value will be n square plus 1 minus 2n. So again we can cancel out 1 and 1. So what will you get n square value as? N square value I'll get it as 4n. The n value will be equal to 4. So in which orbit does the electron belong to? It will belong to fourth orbit. When radius, difference in radius of n plus 1th orbit and nth orbit, if it is equal to radius of n minus 1th orbit, then they're asking what is the value of n. The value of n will be equal to 4. Clear, all of you? Understood, everyone? Let's see next question. In the diagram shown below, two atomic transitions are shown. Lambda 1 is transition, if lambda 1 is given as 4000 angstrom, lambda 2 is given as 500, or I can write it as 5000 angstrom. So you see the transition is made from which state to which state is very important, guys. So here we can take, this is our first state, this is second state, this is third state. In first case, transition is made from E3 to, yes or no? One is 4000, other is 5000. They're asking us to find lambda 3 value, guys. It is also previous year question again. Okay, so if you just look at this situation, first transition is made from third state to first state. Okay, if I write E final minus E initial, I'll get minus. Minus means energy will be emitted, guys. Here I can write it as Hc divided by lambda 1. Then transition is made from second state to first state, if I am not wrong with the diagram. This I can write as Hc divided by lambda 2. Finally, transition is made from, right, third state to second state. So E3 minus E2, you can write it as Hc divided by lambda 3. So what I'm going to do, I will make use of these two beta first. So I'll add both of them. If I add both of them, or we'll separate both of them. If you separate both of them, what are we going to get? E3 minus E2 minus E1 plus E1 you will get, guys. So I'll get it as E3 minus E1, sorry, E3 minus E2 will be equal to Hc by lambda 1. I'm subtracting it, Hc by lambda 2. But what is E3 minus E2 here? Is Hc by lambda 3 will be equal to Hc by lambda 1. Definitely will get such type of questions, guys. Minus Hc by lambda 2. If you take Hc value common, right, so here if you take Hc value common, so Hc divided by lambda 3 if I consider, so Hc divided by lambda 3 value will be Hc, if I take common, it is 1 by lambda 1 minus 1 by lambda 2. So 1 by lambda 3 value will be 1 by lambda 1 minus 1 by lambda 2. So what are we going to get 1 by lambda 3 value as? I can write it as lambda 2 minus lambda 1 divided by lambda 1 lambda 2. Or lambda 3 value can be taken as lambda 1 lambda 2 divided by lambda 2 minus lambda 1. So lambda 1 is given as 4000 angstrom, guys. This is given as 4000 angstrom, right? Lambda 2 is given as 5000 angstrom. 500 nanometer is given. I can take it as 5000 angstrom. The lambda 2 value will be 5000 minus 4000. So what will this turn out to be? This you will get it as, anyhow, you can take it as it is. 20,000 you should get, guys. So this will be 4000 into 5000 divided by 1000. So we can simply cancel out 0, 0, 0, 0, 0, 0. 20,000 angstrom you will get, guys. 20,000 angstrom means I can take it as 2 into 10 power minus 10 power minus 10 is there, into 10 power 4 will be 10 power minus 6 meters, or 2000 nanometer also can be written. Here all of you, it's a very important question again. 1 by lambda 3 will be equal to 1 by lambda 1 minus 1 by lambda 2 in this case, in the diagram which is given to us. For that case, I can write 1 by lambda 3 will be 1 by lambda 1 minus 1 by lambda 2. Is that clear? How much are we going to get? There is no option available. Sorry, I took wrong, I guess. First one is 3 to 2, guys. Then it is 2 to 1. First one is 3 to 2, sorry. Okay, 3 to 2. So you add both of them, guys. If you add both of them, I'll get, here you'll get E2 minus E1. You'll get plus. Here you'll get plus. Here you'll get plus. And third one is from 3 to 1, guys. Here you'll get plus. This will be lambda 2 plus lambda 1. Okay, so in denominator you'll get lambda 1 plus. This will be plus, so you'll get it as 9,000. So 20,000 divided by 9 you will get, which will be triple two. 20,000 divided by 9. So 9 2 is 18. Again 20 will get 2222 angstrom you should get. Clear all of you? 2222 angstrom, or I can write it as triple two nanometer. 222.2 nanometer. Understood, everyone? The 222 nanometer should be the exact answer for that. Clear? So these were the questions from your atoms chapter, guys. Clear, everyone? I think two questions were there. One is based on screening effect. One question was there, and the other one was the last question. We will cross check those questions, and I'll tell you. I'll just see all the chapters, guys, once. Whichever question I have not discussed or I had ambiguity in, I'll just cross check those questions today, and I'll just share the solutions or write solutions for those in tomorrow's class. So this was regarding your atoms, guys. So let us move on to nuclei now. It's a very, very important chapter again, guys. I have shared the notes of nuclei. Whatever things are there, I'll be discussing. But before we move on to nuclei, you can just take a 5-minute break, because we'll continuing this till 10 o'clock, right? It's already 1 hour now. So you just take a 5-minute break and you can come back, guys. Is that clear, all of you? Before we start nuclei, you can just take a 5-minute break and come back. Am I audible, everyone? Is the screen visible? Right. So we will discuss few things related to nuclei again. Right. With questions, I will be discussing majority of the things, guys. The first thing, there is a possibility where question can be asked is there are three ways again in which question can be asked, guys. One will be law of radioactive disintegration, right? The other one will be your types of radioactive decay. Then the other part is nucleus, properties of nucleus, nuclear force, properties of nuclear force, binding energy, and binding energy curve. So that is one part, which is introduction of nucleus. The second part happens to be your radioactive decay, law of radioactivity. The third part is nuclear reactions and types of decay again. So these are the questions. So if you look at the basic thing, now whenever we consider heavy elements, right, they have very less value or low value of binding energy per nucleon. Whichever elements have constant value of binding energy per nucleon, those elements will be called as stable elements. Whichever elements have low value or very low value, they will be unstable. So you can consider those masses, light nuclei, whose atomic masses are less than 30. Binding energy per nucleon is very low. The binding energy per nucleon is very low. It means they are going to be unstable. So what will light nuclei do? They will combine together or fuse together to form a middle mass nuclei. All those masses which lie between 30 and 170. So they are going to have a constant value of binding energy per nucleon. The binding energy per nucleon will explain stability of the element, guys. Right. So these are middle mass nuclei. So usually middle mass nuclei are stable, guys. And if I take heavy nuclei, those masses which are more than 170, binding energy per nucleon is low. So less value of binding energy means they will be unstable. So what will heavy nuclei do? They will undergo fission reactions. They will decay by themselves, guys. The phenomena in which an element decays by itself without being forced to do so by an external agent will be called as radioactivity, is basically observed in heavy nucleus, guys. So let us imagine there is some radioactive nucleus X. It is going to give a stable nuclei Y. Why is the radioactive nuclei disintegrating? Because it is a heavy nuclei, and heavy nuclei will usually have less binding energy per nucleon value. Binding energy per nucleon will explain the stability of the atom or stability of the element. So initially, let us imagine, so X happens to be radioactive, guys, right? So different ways are there in which we write it. So what is the situation now? Initially, let us imagine number of nuclear n naught. This is the situation at t is equal to 0. Y found will be, no Y will be formed. At t is equal to t, what is the number of nuclei left? Let us say n. So how many got decayed, guys? Initially you have n naught. Now you have n only. So how many got decayed? N naught minus n. So whatever of x got decayed, those many of y will be formed. Now after a certain time, t plus dt, let us say, what will be the number of nuclei? Decay only is taking place. So you'll get n minus dn. And this I'll get it as n naught minus of n minus dn. Okay. So number of nuclei of X will go on decreasing, guys. So as per law of radioactivity, it states that the rate of disintegration. What is the rate? If you see initially you have n, after dt time, in a very small time, dn nuclei got disintegrated. So this rate of disintegration, they said it is proportional to number of nuclei left at that instant. Okay. So if you remove the proportionality sign, I'll get, we'll get it as decay constant, which is lambda n. So this dn divided by dt or minus of dn divided by dt, it is called as your rate of disintegration. And what is minus sign indicating over here, beta? Minus sign indicates that as time passes, the radioactive nuclei will go on disintegrating again. So this is also called as activity. It is also called as radioactivity. It is also called as rate of radioactive disintegration, or it is also called as rate of radioactive decay. It will be given as lambda times of n. If you solve for this, you will get different relations. One value will be n is equal to n naught. So basically, if you solve for this, you will get n value as n naught e power minus lambda t. N naught is the initial number of nuclei, n is the number of nuclei at any instant. This is also called as activity, guys. We can write it as A or R. The activity also will exponentially decrease again. It is given as A naught lambda e power minus lambda t. Sorry, A naught e power minus lambda t. And what will this A naught value be? It will be lambda times of n naught. It will be lambda times of n naught. Okay, these three things you have. Then we can also write, if you apply again logarithm, I'll get ln n value will be ln n naught minus lambda t. Right, I'll get ln a value will be ln a naught minus lambda t again. So if you plot n versus t, it will be exponentially decreasing. If you plot a versus t, also exponentially decreasing. But if I plot ln n versus t, it will be a straight line with negative slope and positive intercept. If I plot ln a versus t, it will also be a straight line with negative slope and positive intercept. Okay. The time in which half of the nuclei will get disintegrated will be called as half-life. The time in which 63% will get disintegrated will be called as mean life or average life. Is that clear, all of you? This is basically radioactive disintegration. Because heavy nuclei are going to have less value of binding energy per nucleon, they are relatively less stable. So in order to attain stability, they will break into two middle mass nuclei. Such process is called as nuclear fission reaction. So what is one mean life, guys? One mean life, if I consider average life or mean life, both are same, it will be equal to 1 by lambda, guys. Clear, all of you? So what is it? Half of the initial nuclei will decay? No. How much will decay? 63%, guys. How much will be left out? 30%, 37% will be left out. In one mean life, more than half of the initial nuclei will decay. Half of the nuclei will decay in what time? In average life, guys. Sorry, in half life. Right? Less than half, so it is not there. So what is the situation? So you will get average life or mean life as 1 by lambda. Half life, you will get it as ln 2 divided by lambda, or I can write it as ln 2 into t average also we can write. This is the relation between half life as well as average life. So which of the statement will be correct? In one half life, in one mean life, almost 63% will get decayed. Okay. Next, radioactive sample has 1.6. So at a certain instant, they are saying that these many nuclei are there. After three half lives, what will happen to the number of nuclei? Number of nuclei that will remain undecayed, guys. See, these are the general equations again. N is equal to n naught e power minus lambda t. A is equal to a naught e power minus lambda t. These are general equations. But apart from these equations, we also have the alternate forms of radioactivity, guys. Now, if we focus, so these equations that we have written, right? N is equal to n naught e power minus lambda t, right? A is equal to a naught e power minus lambda t, right? This equation again, ln n will be ln n naught minus lambda t, ln a will be ln a naught minus lambda t. These are general equations. Now, apart from these equations, we also have some equations called as your alternate forms of radioactivity, guys. And what are those alternate forms? Number of nuclei left will be given as n naught divided by 2 power n, right? The activity at any instant will be initial activity divided by 2 power n. Now, because the element is decaying, its mass will obviously decrease. So I can also write it as m naught divided by 2 power n. Here, what is n value? N is nothing but number of half lives, guys. T divided by t half it is. It can also be given as number of half lives. What are they asking? They are saying that if at certain instant 1.6 into 10 power 18 radioactive nuclei are there, how many nuclei will be undecayed after three half lives? Right, so that is the situation they are asking. Number of nuclei that will remain undecayed, they are asking, guys. So what we can do? I don't know the initial number, yes or no? So we don't know the initial number in this situation. So what we can take, beta? At some instant, this is the case. So I can write 1.6 into 10 power 18 will be equal to N value, how can you write? N value. So I don't know what is that instant. The radioactive sample has 1.6 into 10 power 18 radioactive nuclei at a certain instant after 3 half-lives. Okay, you can do it, I guess. No, yaar. There's no need of doing this directly. That instant you assume it as t is equal to 0 only, guys. Okay. So what will I get? Number of nuclei as n naught value is 1.6 into 10 power 18 divided by how many half-lives now? 3 half-lives. So n value is nothing but 2 cube. So which I'll get 1.6 into 10 power 18 divided by 8. 8.2 you will get, guys, which I can take it as 2 into 10 power 17 nuclei will be left after 3 half-lives. Clear, all of you? Yes or no? Then what they have given here in this situation, they have mentioned if r is the radius of the nucleus. Very important case, guys. Always remember, average radius of the nucleus will be given as r naught a power 1 by 3. Will be given as what? Definitely you'll get questions based on this. Last year you got question based on this, guys. Average radius of the nucleus will be r naught a power 1 by 3. Ratio of atomic masses were given. They asked us to calculate ratio of the radii again. This is the average radius of any nucleus, guys. R will be r naught a power 1 by 3. So if I apply logarithm on both sides, what will I get? Ln r value will be ln of r naught a power 1 by 3, which I can also write ln r value will be, it is in the form ln AB. Ln AB can be written as ln A plus ln B. I can also write this as ln r minus ln r naught will be equal to ln A power 1 by 3. Is it in the form ln A minus ln B or not? Yes. So I can write it as ln r by r naught will be, this can be taken as 1 by 3 ln A, guys. So as you can see, they are asking plot of this versus this. Ln r by r naught they are asking, guys. So where is this taken? Ln r by r naught is taken on y-axis. Ln A is taken on x-axis. So is it following y is equal to mx or not? Because it is following y is equal to mx, it is going to be a straight line equation. Clear, all of you? Yes or no? Then a very heavy nucleus has a mass number of 240, right? It has a lower binding energy as compared to that of a nucleus of 120. Lower binding energy per nucleon as compared to that of a nucleus of 120. Same binding energy per 240 is which nuclei? Heavy nuclei or not? So what we can consider, beta? It will have a lower binding energy per nucleon as compared to that of the nucleus of 120. Lower binding energy per nucleon will explain the stability, guys. A is 240 is a heavy nuclei. A is 120 is a middle mass nuclei. Middle mass nuclei usually will have higher value and constant values of binding energy per nucleon. Understood, all of you? Clear? Second one will be the correct statement. Now, variation is given, guys, of two radioactive sample A and B. They're asking us to find out what is the relation between the half lives, guys. Okay. Now, if you want to find out initial number is same or not, initial activity, this is called as nothing but magnitude of dn by dt is activity. If you see initial activity is same or not in both the cases, yes, initial activity is same. For half life, in mean life, how much will be the activity, guys? Will it become 37% or not? So if I take a constant value here which happens to be 37% of the initial activity, right? So I can see that this line is cutting the graphs of two instants, guys. Now this will be your average life. So at this instant you will have average life of B. At this instant you will have average life of A. And what is this instant? This is 0.37 times of initial activity. Is initial activity same for both A and B? Yes, here you can see initial activity for A is equal to initial activity for B. Because initial activity is same, what should be? After one mean life or after one average life, what will activity become, beta? It will become 0.37 times the initial activity. Because initial activities are same for both A and B, 0.37 anyhow is a constant value. So what we can say, activity will also remain same. So activity after one mean life also will remain same. So if I take one activity which is 0.37 a naught, it is possible at two different times, guys. This time for B, this is time for A. So if you look at the graph, what we can say here, we can say average life of A will be more than average life of B. Clear, all of you? Understood or not? Again, whenever you have graph questions, you will do in this manner only, guys. Did you understand? You choose either a constant value of x or a constant value of y. If you choose a constant value of y, you can relate x. If you choose a constant value of x, you can relate y. Understood, everyone? Is that clear? I hope it is clear. Now, this is a very important question, guys. Mx and my denote the atomic masses of the parent nuclei and the daughter nuclei, respectively, in radioactive decay. The Q value for beta plus decay is Q naught. Beta plus decay means a positron will be emitted away. So what is the meaning of beta plus decay? Decay will take place usually in heavy nuclei, guys. If I say Z and A, if it is undergoing beta plus decay, then what is going to happen? The atomic number will get reduced by 1. There is no change in mass number. What will be emitted? Positron will be emitted. Apart, along with positron, always neutrino will be emitted, guys. Okay. In the same manner, if I take beta minus decay, let us say, in beta minus decay, what will happen to atomic number? Increases by 1. Mass number, no change. It will be accompanied by release of electron. Along with electron, always antineutrino will be. So neutrino and antineutrino are just like elementary particles. They are taken for conservation of the linear momentum, guys. Conservation of angular momentum. Here in the same manner, if it is undergoing alpha decay beta, then what is going to happen? It is not x here. You please take it as y. So it will be, what will happen in alpha decay? Atomic number will get reduced by 2, mass number will get reduced by 4, alpha particle will be decayed, as well as some energy will be released, which is called as disintegration energy. In the same manner, if you take gamma decay, guys, what will happen? Nucleus from excited state will come to nucleus in ground state with the release of energy, which will be in the form of gamma rays again. So is there any change in atomic number or mass number? No. And always remember, whenever beta decay is given, whenever which decay is given, beta decay is given, you will usually take beta minus decay, guys. In beta plus, atomic number reduces by 1, no change in mass number. In beta minus, atomic number increases by 1, no change in mass number. In alpha decay, atomic number reduces by 2, mass number reduces by 4. In gamma decay, very simple logic, an excited nucleus is coming back to ground nucleus, ground state nucleus, with the release of energy, and that energy will be in the form of gamma rays. So no change in atomic number and mass number. Now what is given here? Atomic masses are given, guys. It's a very, very important question. Mx is uh, Mx and My will denote atomic masses. So first of all, you please tell me Mx will contain what, guys, in general. So if I take Mx here, Mx and My denote the atomic masses of the parent and daughter nuclei in radioactive decay. Q value for beta plus decay is Q naught. If Me denotes the mass of the electron, the value of Q naught is how much they are asking. So what is happening to X here? X is decaying to form Y. It is undergoing beta plus decay with the help of what beta? Positron, right? And neutrino will be released. Now, what is Q value? Q value will basically be energy of the products minus energy of reactants, guys. Okay. X is given. Here we should take nuclear masses. We should not take atomic masses, guys. Okay. Mx is given as the atomic mass. It is not nuclear mass. Okay. So what I can say, let us say m dash x happens to be the nuclear mass. Here m dash y happens to be the nuclear mass of y. Plus positron will have same mass as that of electron but a positive charge. So this is mass of electron or not? Now, what is Q value? Q value happens to be energy of products minus energy of reactants. Or I can write, because from the famous Einstein's mass energy equivalence, we know binding energy will be given as delta M into C square, mass defect into C square. Okay. So what we can take beta here, I can take it as, if energy is being released, energy is released means mass of reactants will be more than mass of products, guys. Okay. And if energy is absorbed, then mass of reactants will be less than mass of products, guys. So let us take whatever the situation is. So here, what is mass defect now? I can take it as my dash plus me minus mx dash, and I'll write it as into c square beta. Clear? Now my is what? My dash is nuclear mass. How will I get nuclear mass beta? Very simple logic. How will I get nuclear mass? Nuclear mass, I'll get atomic mass minus number of electrons mass or not. So what is nuclear mass? We can say atomic mass. How much is it? My minus which mass here? Number of electrons. How many number of electrons are there? If it is undergoing beta plus decay, it has z minus 1 electrons, guys. Z minus 1 into mass of electron. Is that clear? Plus me you can write. So I'll just take it to the left hand side, little bit left hand side, guys. So I'll get it as, see, this is nuclear mass. How can I write nuclear mass? It is atomic mass minus mass of the electrons. How many electrons is it containing? Z minus 1. Plus me you can write, which is mass of positron here. Minus of what is mx dash here? It is nuclear mass. How will I get nuclear mass? It is atomic mass minus how many electrons I'm assuming? Let us say Z electrons are present with it. Into what will you write beta? C square. So what are we going to get here? My minus Z into me plus me plus me again minus mx plus Z into me into what beta? C square. अब देखो यहाँ से what we can cancel out, plus ZME minus ZME gone or not. So what we can write here, it will be my minus mx, right, minus or plus 2me into c square we can write. This is your q value, guys. So if I take minus sign here, if I take minus sign beta, so what are we going to get? If I take minus sign, what are we going to get? Mx minus my minus 2me into c square. And what is this minus sign indicating? It indicates that energy will be released, guys. Second option will be the answer for that. Understood, all of you? Clear, everyone? mx and my are given as atomic masses. But while I write binding energy equation, we'll take nuclear masses, guys. Is that clear, all of you? It's a very important question again. Very good question also. Let us see the next question, guys. They have given a neutron strikes oxygen nucleus, okay, with the subsequent emission of an alpha particle. The atomic number and mass number of element produced are what they are asking. I'll directly write the equation here. What is the equation? Neutron is what beta? H12. It is going and colliding with oxygen, right? Subsequent emission of alpha particle. Alpha particle is helium nucleus, guys. Inside helium nucleus, you are going to have 2 neutrons and 2 protons. It will not contain electrons, guys. Alpha particle is helium nucleus. So let us say X is the element that will be released. Always remember, in any chemical reaction, you will have conservation of mass and conservation of energy. If you talk about conservation of mass, here you have 1 and 8. Overall, you have 9. Already we got 2 here. So what will be the situation? We'll get atomic number as 7. 2 plus 16, we already got 18. 18, and here you have 4, guys. So what should be left out? 14 should be left. So the element which is formed will have how much atomic number? 7 will be the atomic number and 14 will be the atomic mass or mass number. Understood, all of you? Question, if you see. The half-life of a radioactive isotope is 100 years. It decays to another element Y, which is stable. The two elements X and Y were found to be in the ratio 1:31 in a sample of a given rock at some instant. Initially, total nuclei will be X only, guys. Initially, there will not be any nuclei of Y. Now they are saying 1 nuclei of X is there and 31 nuclei of Y are there. Okay. So they're asking what is the age of the after some time. So please tell me general formula. What are the number of nuclei left in disintegration process? N naught e power minus lambda t. How many nuclei got disintegrated, guys? Initially you had N naught. Now you have N left. N is the number of nuclei left. N naught is the initial number. 10 chocolates you had. Now you have 2. How many you gave? 8. So 8 got disintegrated. Whatever getting disintegrated, those many of Y will be formed or not. So what will this be, guys? N naught minus N naught e power minus lambda t. So I'm going to get it as N naught into 1 minus e power minus lambda t. Is that clear? So these will be the nuclei of X at any instant, and these will be the nuclei of Y at any instant. Now, what is the ratio they are saying? They are saying that nx divided by ny happens to be 1 by 31. So from this, what we can write, beta? N naught e power minus lambda t divided by N naught into 1 minus e power minus lambda t will be equal to 1 by 31. So we can cancel out N naught and N naught from this. So what are we going to get? Implies 31 e power minus lambda t should be equal to 1 minus e power minus lambda t. So 32 e power minus lambda t, you will get it as 1. Okay. So what we can also do, I can also write this, you can send in denominator, I'll get e power lambda t value will be equal to 32. Yes or no? You can write e power minus lambda t as 1 by e power lambda t. If I apply logarithm on both sides, what will I get? Ln e power lambda t will be equal to ln 32. 32 is nothing but 2 power 4 or not, guys? Sorry, 2 power 5 or not? What I'll get? Ln e power lambda t will be ln 2 power 5. So which I can write it as ln e should be equal to 5 ln 2. Okay. So what will be the time? Ln e value will be anyhow 1, guys. So what will be the time I'll get? 5 into ln 2 divided by lambda. What is this ln 2 divided by lambda? Is it half-life or not, guys? Yes. So I can write it as 5 into half-life. So what is half-life given? 100 years is given, I believe, if I'm not wrong. So what will be the time after which the ratio will be 1 is to 31? You will get 500 years, guys. See, instead of using n is equal to n naught e power minus lambda t, you could have used n is equal to n naught divided by 2 power n also. That is not going to be any problem, right, in order to obtain the answer. I hope it is clear, all of you. Yes or no? So after what time will the rock have the constituents in the ratio 1 is to 31? After 5 half-lives of X, which is 500 years. Clear, all of you? What is this? If we talk about N, what is N here, beta? It is number of nuclei left at any instant. So number of nuclei left at any instant will be N naught e power minus lambda t. And what is N naught into 1 minus e power minus lambda t? It is number of nuclei of Y formed, or number of nuclei decayed we can consider, guys. Clear, all of you? Yes or no? Hope it is clear. Expression if you see. In a radioactive material, activity at time t1 is 1 by 2 lambda. 1 by 2 lambda is A1. At a later time, it is A2, where lambda is a decay constant. The relation between A1 and A2 they are saying. So what we can write A1 value as, beta? I can write A naught e power minus lambda T1. Yes or no? And what will A2 value be? It will be A naught e power minus lambda T2. So what is T1 value given? 1 by 2 lambda it is given. So what will I get? A naught into, because it is given as 1 by 2 lambda, or lambda into T1, I can write it as e power minus 1 by 2. And what is lambda 2 T2 value given? T2 value is given as 1 by lambda. So I can write it as e power minus 1, guys. So if you divide both of them, what will I get? A1 by A2 value will be equal to, anyhow, these two will get cancelled out. I'm just dividing both of them. We can cancel out A0 and A0. I'll get e power minus 1 by 2 divided by e power minus 1. So I'll get A1 value as A2 e power plus 1 by 2, guys. This will be the relation between A1 as well as A2. So A1 value will be, so I can say this will be correct. Or I can write here, from this you can write A2 value will be A1 e power minus 1 by 2. Understood all of you? Yes or no? Very good question again. Same manner. If you see the other question, am I audible everyone? That's right. So let us see the next question, guys. They are saying that radius of a nucleate X is measured to be twice the radius of BE. So here what they are saying, very direct question again, radius of X is given as 2 times the radius of beryllium. What is the number of nucleons in nucleate X? Now, nucleons means nothing but their mass number, guys. How is radius related? It will be given as R naught A power 1 by 3 will be equal to 2 times of R naught. What is beryllium mass here? 9 power 1 by 3, guys. Yes or no? So what we can take in this situation? Can I cancel out R naught value? Yes. So what are we going to get? A power 1 by 3 value will be 2 into 9 power 1 by 3. If I cube it on both sides, I will get A value as 2 cube into 9. So A value will be 8 into 9. So the number of nucleons present with the nucleide X will be how much, guys? They are going to be 72. Clear? Very important formula. Average radius of a nucleus will be R naught A power 1 by 3. But if you take densities of any nucleus, guys, you take any nucleus density, all the nucleus will have same density. The order will be 10 power 17 kg per meter cube, right? Nucleus is highly dense, and every nucleus will have same density, 10 power 17 kg per meter cube. But masses of every nucleus is different, radius of every nucleus is different, density will remain same, guys. Understood all of you? Yes or no? And here in this situation they're asking q value of the decay is how much they're asking, guys. So again, you can write either mass of reactants minus mass of products into c square. If you are writing mass of reactants minus mass of products, it means energy is released. If you are writing mass of products minus mass of reactants, it means energy is absorbed, guys. So basically we take energy released only. Q value is nothing but energy released we take, guys. So how do we represent Q value here? What is mass of the uh, reactants here, guys? How much is the mass of the reactants? If you take it as m, the mass of X you can take minus what is mass of product here, right? M of Y. Also you have electron, guys. Yes or no? Into what will you write? C square. Clear all of you? Yes or no, everyone? So what are we going to get Q value as? You will get mass of the nucleus X minus mass of the nucleus Y minus mass of electron into C square. Understood, everyone? So if I'm writing reactants minus products, what does it mean? It will be energy released, guys. This would be the answer for it. Clear all of you? Yes or no? Next, if you take 5.2 into 10 power minus 13 joules of energy is released per fusion reaction. The mass of the deuterium consumed in a fusion reactor of power 1 megawatt, they are asking, guys. Okay, so how will you do it again in this very simple situation? In one fusion reaction, this much energy is released. So how much mass will be consumed in order to get, so what is power of a reactor? Always remember, power of a reactor will be energy released per unit time. Okay, so I want in one day, so what is the total energy release? So if already 5.2 into 10 power minus 13 joules is given, right? This is energy released in one fusion, guys. Like that, let us say n fusions are taking place. So what would be the value of n here? You will get it as P into T divided by E, guys. Power of the reactor is already given 1 megawatt, which is 10 power 6. Each day you will have 24 hours. Each hour you will have 60 minutes. Each minute you have 60 seconds. What is energy released in one fusion reaction? 5.2 into 10 power minus 13 joules, guys. So if you send it to numerator, you will get it as 12, 144, 288. You will get, guys, 288 divided by 5.2 into uh, 10 power 6, 10 power 8. You will have 10 power 21. You will get, guys. Okay. Or I can write it as 28.8 divided by 5.2 into 10 power 22. These many fusion reactions are taking place. Okay. Now they are asking the mass of H12 consumed in a fusion reactor. For one fusion, you see how much mass is consumed? 4 grams, guys. Yes or no? So what will I get overall this as? 5.2 into, it will be more than 5 only, guys. Yes or no? Near about 5.5, something like that. So if you see in one fusion reaction, for one fusion reaction, how much mass is consumed? You can consider 2 grams and 2 grams. How much mass is consumed, guys? 4 grams is consumed. Yes or no? Or to be precise, 4U is consumed, guys. Now what they are saying, in 28.8 divided by 5.2 into 10 power 22, how much is the mass consumed? Yes or no? Are you getting my point, all of you? So first of all, we have found out energy released in one fission is 5.2 into 10 power minus 13. Total power delivered by the reactor is 1 megawatt in 1 day, guys. So in 1 day, time is 86,400 seconds. Into power we have taken divided by energy. I'll get number of fusions, guys. So for one fusion reaction, we require 4U mass. For these many fusions, how much mass is required? They're asking. What will X value be, beta? I can write it as 28.8 divided by 5.2 into 10 power 22 into 4U you will get. Okay. So X value will be 28.8 into 4. U value is anyhow 1.67 into 10 power minus 27 kgs you will get, guys, which I can write it as 10 power minus 22 in 22 into minus 27 will be minus 5 you will get. Divided by how much will this be? 5.2. So I can take 4 ones, 4 13s you will get, guys. So I can also take it as X value will be near about, I think, how much will you get this as? This is in kgs again. If I want to get it in grams, so I can take it as, I can take this as 0.288 divided by 1.3 into 1.67 into 10 power minus 3 kg I will get, which I can take it in grams again. So how much will this be? 1 point something you will get, guys. It will be 1 point something. So it will be just more than 10 power minus 5 we got, no? Is this correct, all of you? 4 and 4, 1.3 we took. 288 by 13 you can take, guys. So if you want to take 288 by 13, 288 divided by 13 we can write. So we know 13 ones, 13 twos, 26. Again you will get 28, 13 twos, 26, 20 you will get 1, and 70 you will get 13, 565 you will get, guys. So 22.1 you will get, somewhere near about 22.1. Now 22.1 means X value will be, how much I can write? 10 power minus 5 is there, no? So if I take it as 0.221 into 1.67 grams you will get, guys. So how much is 1.6 times of 0.2 or 1.7 times of 0.2? Just check. Will it be 1.4, something like that you will get, no? How much we got? 0.221 into 1.67. I'm getting 0.36 only. Is there any mistake that we have done? Just check. Procedure, did you understand, all of you? Did I do any mistake here? Here we got uh, the power of a reactor will be energy release per unit time. In one fusion, it is taking E. So in N fusions, N into E divided by T. I found out the number of fusions here, guys. We got PT by E, 10 power 6 into 24 into 60 into 60 divided by 5.2 10 power minus 13. So we got this as 10 power 8 divided by, achha, I took into 10 by 10 if you do. Yeah, 28.8 you will get. Correct only because, sorry, I did mistake here. Into 3 you will get, guys. I took 6 6 are 12. 6 6 8 is 36, no? So please write into 3 you will get everywhere. So I think answer will be 1.1, guys. Into 3 you can take. So you'll get it as 1.1 grams. I hope you understood the procedure of solving the question. Right, let us see the next question. Uranium 238 is given. Hypothetically undergoes 9 alpha and 8 beta decays. Right, so uranium 92, 238 is there. First of all, let us say it is undergoing 9 alpha decays. In each alpha decay, what is going to happen? It will become some x. In each alpha decay, 2 decrease in your atomic number. 9 alpha decays means 18 decrease or not. So 92 minus 18, how much will I get it as, guys? Will you get it as 66? Sorry, 76? Yes or no? Right? And what will happen to mass number? Gets reduced by 4. So 9 4s 36 it will get reduced, guys. So I am going to get it as 202 or not. Then now it is undergoing 8 beta minus decays. Beta minus decays means mass number no change, but atomic number will get increased by how many times, guys? By 1 time for 1 beta minus. So for 8 beta minus it will get decreased by 8 times. So I'll get eventually 84, and here I'm going to get 202. So what will be the answer, guys? You will get did I do any mistake, guys, here? 9 alpha means 18 should get reduced, no? So this will be 74. 74 plus 8 will be 82, guys. So you are going to get lead 82 to not 2 as the resulting answer, guys. Very important case again. In alpha decay, atomic number gets reduced by 2, mass number gets reduced by 4. In beta decay, usually if generally beta decay is given, you should take beta minus only, guys. Right? And if beta plus is there, atomic number reduces by 1. If beta minus is there, atomic number increases by 1. No change in mass number. In a nuclear reactor, moderators slow down the neutrons which come out in fission process. The moderator used have light nuclei. Heavy nuclei will not serve the purpose because elastic collision of neutron. Right, I'll just cross check this question also, guys. Slow down the neutrons which come out in a fission process. The elastic collision of neutron with heavy nuclei will not slow them down. Yeah, it is one of the case. First one will be possible. Substances which have heavy nuclei do not occur in liquid or gaseous state at room temperature. Some heavy nuclei you see, liquid or gaseous state, I'm not sure. The net weight of a reactor would be unbearably high. They will break up. I think first option would be probably the correct answer, but anyhow, I'll just cross check that question, guys. Which among the following can emit gamma radiations? Will emit beta? Nucleus will emit. Excited nucleus. These are atoms and ions, right? You will have gamma decays again, but gamma decay usually happens in excited nucleus, guys. Clear? This is also possible, right? But because we are focusing in this situation, so whenever just like atoms have different energy levels, nucleus also has different energy levels, guys. Whenever a nucleus is making a transition from excited state, higher energy level, to ground state, it will emit energy which will be in the order of mega electrovolts, guys. In atom you will get hardly electrovolt, but in nucleus you will get it in the order of mega electrovolt, guys. The excited nucleus will usually give gamma radiations again. The set which represents isotopes, isobars, and isotones. What is the meaning of isotopes? Same atomic number, different mass number. Yes or no? So as you can see, this is wrong. Yes or no? This is also wrong. So either first or second may be correct. What are isobars? Same mass number but different atomic number. So automatically this will be wrong. So what would be correct, beta? Your second one will be correct. See, same atomic number, different mass number. Same mass number, different atomic number. What are isotones? They have same number of neutrons, guys. 197 minus 79 if you do, 198 minus 80 if you do, you will get the same value again. What percentage of radioactive nuclei is left after 6 half-lives? What is the formula that we will apply? N value will be n naught divided by 2 power n, which is n naught divided by 2 power 6, which is n naught divided by 64. This is the number left. What is the fraction left? N by n naught, which is 1 by 64, guys. What is percentage left? N by n naught into 100, which will be 1 by 64 into 100. Near about 2%, you can say, will be left. So your answer should be 1.56%, guys. Clear, all of you? Alternate forms of radioactivity, very important formula again. If nuclear force between two protons, between proton and neutron are pp and pn, nuclear force, always remember they are charge independent, guys. They will be same between proton, 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 neutron, neutron, proton, neutron, neutron. So they are going to have same value, guys. FPP and FPN same over here. Is that clear, all of you? Nuclear force is charge independent. Whether you take two protons or two neutrons, one proton, one neutron, one neutron, one proton, the force is going to remain same. Understood, everyone? I hope it is clear. Next question. Nucleus has 3 protons. Lithium nucleus has 3 protons and 4 neutrons. Right? The mass is given. They're asking us to find mass defect, guys. So whenever we talk about lithium, it has 3 protons. 4 neutrons means overall nucleons will be. So when it is decaying, guys, it will give rise to 3 protons. It will give rise to 4 neutrons and some energy will be released again. They're asking us mass defect again. So what is mass of proton given? I can just multiply here, guys. This total mass will be 3 into mass of proton is 1007277. Such type of questions will not be given in NEET again anyhow. 4 into what will I get here? 1.008665. Okay. And what will this be value? This value will be anyhow 7U, guys. Okay. So this you can take it as U and U. Clear, all of you, guys? So what is mass defect now? Mass defect is simply difference between their masses. So I don't know whichever is greater. So let us imagine 7U is greater or whatever it is. Anyhow, this value will get more than 7, guys. So I can write it as 3 into 1.007277U, right? Plus 4 into 1.008665U minus 7U will be your mass defect. Okay, so whatever it is, just cross check it and you will be getting the answer, guys. Okay, understood, all of you? The next case, if you see, how long can an electric lamp of 500 watt be kept glowing by a fusion of 2 kg of deuterium? You see, 4 grams of deuterium or 4U of deuterium. From 4U, how much energy are we obtaining, beta? 3.27 million electrovolt is being obtained. Now they are saying 2 kg. So for 2 kg, how much are we going to obtain? Let us say X. So what are we going to get the X value as? X value will be 3.27 mega electrovolt can be written as 10 power 6, 1.6 into 10 power minus 19. These many joules into 2 divided by 4U you will get. U value is 1.67 into 10 power minus 27 kg again. So what will get cancelled over here if you see? Right, 1.6 and 1.6 directly, generally you can say it is cancelled. So you'll get 0.2 ones, 2 twos you will get, which will be 0.16, 1.6 you will get, which you can take it as approximately 2, guys, again. So what is this? 10 power minus 13. If you send this to the numerator, it will become 10 power 14 again. Right? So what are we getting here, guys? I'm going to get it as near about 1.67, something like that. 1.63 into 10 power minus 13, you got 10 power 14. This much joules of energy is released. Right? They are saying for how much time can electric lamp of 500 watt be glowing? So we know the total power emitted will be energy transmitted or energy released per unit time. What we can write time value as, guys, it is energy released divided by power. So what will I get the time as? Energy, total energy we got 1.63, near about 1.8 you will get, guys, 10 power 14 divided by power is how much? 500 watt. So I'll get it as 10 power 12 here. 5 is there, zero point 0.3 something. 0.3 into 10 power 12 we will get, guys, which will be first option, I guess. So the time you will get it as 3.15 into 10 power 11 seconds. This will be the answer. Very important questions, guys. All these are important questions. Whichever power, energy, these questions we are doing, these are very, very important again. And just now I have said you, like atom, when a nucleus is in excited state, spontaneously decays to ground state. Photon is emitted. What will be the difference in the energy levels? It will be in the order of million electrovolt, guys. Understood, everyone? Just now we have seen again regarding decays also. The emission of electron in beta minus is accompanied by emission of antineutrino. Is that correct statement? Beta minus electron will be always antineutrino only. Correct only, guys. Emission of in beta decay atomic number Z remains unchanged. Wrong, no? In beta decay, either it will increase by 1 or decrease by 1. It will increase by 1 for beta minus, it will decrease by 1 for beta plus. Electron will always be accompanied by antineutrino, correct? Positron will always be accompanied by neutrino, correct? Free neutron, unlike a free proton, is unstable. This is also correct, guys. So which is wrong here? Beta minus beta decay, atomic number remains unchanged, will be wrong. Radioactive substances A and B have decay constants 4 lambda and lambda respectively. Similar type of question you got in 2017 NEET, guys. Right? They have same number of nuclei initially. The ratio of number of nuclei of A to number of nuclei of B will be 1 by E square after how much time interval? So what is the number of nuclei left? We know n naught e power minus lambda t. The nuclei of A will be, they have same number, guys, n naught e power minus, how much is the decay constant of A here? Decay constant of A is given as 4 lambda into t. What will be number of nuclei of B left? Initial number is anyhow same, e power minus lambda into t. So if I divide both of them, what are we going to get, beta? Anyhow, n naught and n naught will get cancelled out. So what are we going to get? We will get Na divided by Nb value as e power minus 4 lambda t divided by e power minus lambda t. If I send this to the denominator, I will get e power 4 lambda t. So I will get e power 4 lambda t minus lambda t will be 3 lambda t. And what is the ratio of Na by Nb given? It is given as 1 by E square. So as you can see, rest all are same only. So you can just directly equate their power. 3 lambda t value will be equal to 2. T value will be 2 divided by 3 lambda, guys. Clear, everyone? After this much time, the ratio of number of nuclei of A to nuclei of B will be 1 by E square. Understood, all of you? Yes or no? Again, very important concept. Radius of nucleus, guys. Radius of X is 3.6, it seems. What would be the radius of Y? This you take it as A1, guys, here. So what will be radius? Radius is proportional to A power 1 by 3. So R2 divided by R1, I can write it as A2 divided by A1 whole power 1 by 3. So if you look at this, A2 by A1 is how much, beta? 125 divided by 27 whole power 1 by 3. 125 is 5 cube. 27 is 3 cube whole power 1 by 3. I will get it as 5 by 3, beta. So what will R2 value be? It will be 5R1 divided by 3, which is 5 by 3 times of, what is R1 value given? It is 3.6 for me. 1.2 into 5, you will get it as 6 for me, guys. radius of a nucleus is proportional to 1 by mass number raised to the power 1 by 3, guys. Same case, let us take the next question. What they have given? The activity of a sample is measured as n naught counts per minute. Activity is given as n naught, guys. And n naught by e square counts in 10 minutes. What is the time at which the activity reduces to half of the value? They are asking us to calculate the half life, guys. So what is initial activity? Initial activity is given as n naught per minute. You can take it as n naught. And what is activity after a certain instant? It is becoming n naught divided by e square. So what we can write, a value is a naught e power minus lambda into t. So what is this? N naught divided by e square. This will be n naught e power minus lambda t. What we can cancel out? N naught and n naught will get cancelled out. So implies you can write e power minus 2 will be equal to e power minus lambda t. I can write lambda t value as how much beta? 2. In how much time they are saying? They are saying it is reducing in 10 minutes, guys. So what will be lambda value here? 10 minutes we will get, which will be equal to 2. So lambda value will get it as 1 by 5. So what is t half they are asking? T half value, as you all know, it will be ln 2 divided by lambda. So I'll get the answer as 5 ln 2, guys. Ln 2 is nothing but log to the base e. So I'll get the answer as 5 log 2. Clear all of you? Understood everyone? I hope you have understood. So activity can be given as a naught e power minus lambda t, right? So there, from there we found out the value of lambda. So after 10 minutes, they said that activity became n naught by e square. So that is what we have solved. Next case, if you see, again this already we have done. This question we have done already, so I think we can do this. H12, H13 is giving He24 and neutron, guys. If the binding energies are given, guys. So H13 it is given as E1, H12 is given as E2, and H E. So what is situation here? You can take H12 and H13 will give rise to He24 as well as neutron. Yes or no? So for this energy is given as E2, for this energy is given as E1, for this energy is given as how much here? Energy is given as E3. They're asking what is the energy released? Energy will be released only when energy of reactants is more, guys. So what is the energy released here? The energy released, if they are asking, then you can write it as E1 plus E2 will be energy of reactants. Already binding energies are given, so directly we can write, guys. If they were binding energy per nucleon, then binding energy for H12 would have been 2E2. For H13 would have been 3E1. And for helium, it would have been 4E3. If E1, E2, and E3 were binding energy per nucleons, in that case, I am saying. But here already they are given as binding energy, so I can write E1 plus E2 minus E3, guys. This would be the energy released. Always remember, energy is released means energy of reactants will be more than that of energy of products, guys. You have already done this question just now, yes or no? They're asking which of the following is correct. Mean lives are given. Initial activities, again you see they are same, guys. If initial activities are same, they're talking about mean lives. So 0.37% you can take again. Just now we have done the similar question. So I'm not explaining it, guys. So what is the answer for that? Tau of A will be more than tau of B. Mean life of A will be more than mean life of B. This also we have done just now. Yes or no? And what did we get this as? I think we got mx minus my minus 2me. This one, third one we got, I guess. Choose the incorrect statement they're asking, guys. Multiplication factor is 1. The operation of the reactor is said to be critical. Yes, it is correct, guys. Control rods are made up of neutron absorbing material. See, there are 4 major parts in nuclear reactor. First is fuel. What can be considered as fuel? Easily fissionable material. Usually you take uranium 235. as the fuel. Then we have moderators, guys. What will moderators do? They're going to slow down the moving neutron. Okay. Then we have control rods. They are going to capture the slow moving neutron. Right. Then we have coolant, and we have shielding. Okay. Right. So what will be coolant, guys? At normal temperature, water can be taken as coolant, or water or heavy water. At high temperatures, liquid sodium should be taken as coolant. Control rods, basically they are made up of boron or cadmium rods, guys. And graphite is usually taken as moderator. In some reactors, water is also taken as moderator, guys. Okay. Second case, control rods are made out of neutron absorbing materials such as cadmium. Correct? Yes, boron or cadmium rods. Water is used as operator in Apsara reactor. Yes, in some reactors, usually graphite is moderator, guys, but they will choose water also as moderator. Then, for thermonuclear fission reactions, temperature of system should be of the order of 10 cube Kelvin to overcome the Coulombic repulsion. I think this should be more than 10 cube Kelvin, guys. Okay. So I think fourth option would be wrong statement in this. Average binding energy per nucleon is constant and is equal to 8 million electrovolt per nucleon for most of the nuclei. This is because nuclear force is, right. Is it charge dependent? No. Is it long range force? No. Is it a central force? No. It shows saturation property, guys. Nuclear force is a non-central force. It is charge independent force, and it is a short range force. Because these three properties of nuclear force is wrong, automatically the answer will be fourth option, guys. Clear, everyone? Binding energies of nuclei X and Y are given. Two atoms of X gives one atom of Y. So what is given to us? Binding energies is given. What are this? E1, E1. This is what? E2. So what is Q value of energy released again? Energy of reactants. Energy is released means reactants energy will be more, guys. Already binding energies are given, so I'll write it as 2E1 minus E2. Clear, all of you? Right. Next case they are asking, consider the following equation. Mass of H12 is given, mass of helium is given. Q value in this process they are asking, guys. Now, first of all, we will find out the mass defect in this case. Energy release means it will be mass defect into C square. Because energy is released, they have given. So what I can write better, it will be mass of the reactants minus mass of the products into C square. And always remember, if masses are given in atomic mass unit or unified mass, instead of C square, I can directly write 931.5, guys. So what will be mass of reactants? I have 2 into, I can write 2.0141 U minus, what would be mass of products? 4.0024 U into C square. What I'll get? 4.0282 U minus 4.0024 U into what will you get? C square. Usually when whenever mass defect is given in U, guys, I can write U value. I'll tell you how much will this be. 82 you have, no, so you will get it as 8 again. Then here you will get 5. This will be anyhow 2 only, I think. Right, so you'll get it as 0.0258 U into C square. So how can I write this U as? Am I right, guys? I hope I am correct again in this situation. What we can write? 0.0258 U value will be given as 931.5 MEV divided by C square, again into C square we have, guys. So this will be 0.0258 into 931.5 MeV. Okay. So almost you can just solve for this, you will get the answer again. Clear, all of you? It will be near about 20 MeV, I guess. Yes or no? It is 2 by 100 you can take. 2 by 100 means near about 20. I think 24 you will get, I guess. Just cross check that, you will get it, guys. Because it's 2.5 times, no? So I think 24 MeV will be the answer. Always remember, 1 U will be given as 931.5 MeV divided by C square. Graphite and heavy water are two moderators used in nuclear reactor. The function of the moderator, what does it do, guys? It will slow down the neutrons. Control rods will capture the slow moving neutrons. Coolant will remove the heat from the core of the reactor. The radioactive process can decay by two different processes. The half-life of the first process, this is called as simultaneous decay, guys. And always remember, in case of simultaneous decay, suppose if there is one radioactive nuclei X, in one process it is decaying to form A, in other process it is decaying to form B. Lambda 1 is the decay constant in this process, lambda 2 is the decay constant in this process. Then I will give effective decay constant as lambda 1 plus lambda 2. Okay, or I can write 1 by T half effective will be 1 by T half of 1 plus 1 by T half of 2, because we can write ln 2 as we can write lambda as ln 2 divided by T half, guys. So half lives are given in this. What will be the effective half life? The effective half life, if I take, it will be equal to 1 by T1 plus 1 by T2, which can be taken as T2 plus T1 divided by T1 T2. This is our 1 by T half effective, guys. So I'll get T half effective as T1 T2 divided by T1 plus T2. Clear, all of you? Very important case in simultaneous decay, guys. Right? Whenever a radioactive nuclei simultaneously decays into two stable nuclei, then effective decay constant will be sum of individual decay constants. 1 by T half effective will be 1 by T half in first process plus 1 by T half in second process. I can also write 1 by T average effective. Mean life also, guys. 1 by T average effective will be 1 by T average in first process plus 1 by T average in second process. Very important concept of simultaneous decay. Just remember this case again. We can prove that also, but as of now, it's not that much necessary, guys. Right. FPP, FPN, FNN denote the magnitudes of net force by a proton on proton. They're not talking about the nuclear force, guys, here. Right? They're talking about net force acting. So between proton and proton, you will have electrostatic force also of repulsion. Yes or no? Between neutron and neutron, you are not going to have any force. Right? So by a proton and proton, by a neutron and neutron respectively, neglecting the gravitational force, when the separation is 1 Fermi, then choose the correct option they're asking. 1 Fermi usually is 10 power minus 15 meters, guys. So in such cases, here you should also take into account the repulsion of between proton and proton, guys. So 1 Fermi is short range only. The short range means you are going to have strong nuclear forces, guys. The nuclear force of attraction is more. If I take the resultant force, here you will not have between proton and neutron no electrostatic force. Here also no electrostatic force. So FPN and FNN both will be same. FPN and FNN both will be same. Okay. But here, because between proton and proton, I should counter the electrostatic force of repulsion also. So the net force will become less than the nuclear force of attraction. So here I can write FPP value will be less, which will be same, for PN and NN. Clear? Understood, all of you? Because net force they are saying, they're not talking about nuclear force, guys. If nuclear force was given, directly my answer would have been first option. But they are saying net force here. So net force is given means on proton, there will also be repulsion. Attraction due to nuclear force, repulsion due to electrostatic force. So I need to counter that repulsion. So the net force will become less than the nuclear force of attraction. Next case, if you see this question, let us,
FPN equal to FNN.
because there is no electrostatic force no between. Electrostatic means both of them should be charged. Neutron doesn't have charge. An approximate electrical potential energy due to the electric repulsion between two nuclei of C12 when they touch each other. When they touch each other, they are saying, guys, So what will be the nuclei? Nuclei, they are saying. Nucleus will have positive charge or not. So how much positive charge? Plus 6e. Other one is also plus 6e. They are touching each other. Means what will be the separation between their centers? The separation between the centers will be 2r. If I just take, because radius is given as 2.52, if I multiply with, so I'll get it as 5.04 for me, guys. So when two charges are separated by a certain distance, what will be the potential energy? I can write it as q1 q2 divided by 4 pi epsilon naught r. Yes or no? So what is q1 here? 6e and 6e. Nucleus, they said, guys. Nucleus will have positive charges only. So what I can write, 6e into 6e divided by 4 pi epsilon naught, and r value will be 5.04 into 10 power minus 15, because 1 Fermi. So what is 1 by 4 pi epsilon naught? 9 into 10 power 9 into what we can write here, 36. What will be e square, beta? 2.56 into 10 power minus 38 you will get, because e value is 1.6 into 10 power minus 19. If I just square it, divided by 5.04 into 10 power minus 15 you will get, guys. Okay, so what I can do, this is almost ones, this is almost twos, guys. Two ones, and what we can take, to 18 you will get. Yes or no? Two ones, two 18s you will get. 18 nines, how much are we going to get, guys? I think you will get it as near about 162, I guess, if I am not wrong. So you'll get it as 162. 1.64 should be the answer, guys. So 162 into 10 power 9, 10 power minus 38 will be 10 power minus 29. 10 power minus 29 minus 15 here, sorry. So you'll get as 10 power minus 14, guys. To which I'll get it as 1.62 into 10 power minus 12 joules. Whenever two charges are kept at some separation, the expression for potential energy will be kq1 q2 divided by r. You should take the magnitudes as well as the polarities, guys. For calculation of force, you should take only magnitudes again. Because if you see, in a radioactive sample, the fraction of initial number of nuclei which remains undecayed after n mean lives. So what will be number of nuclei left? 2 power n. So what will I get, beta? N mean lives, they said, not half lives, guys. So what we can write, number of nuclei left will be n naught e power minus lambda t. N is the number of nuclei left, n naught is the initial number. What is the time now? N mean lives, they are saying. So n into t average you can write, guys. So n divided by n naught, if I take, I'll get it as e power minus lambda n. And what is t average, beta? It is 1 by lambda. So I'll get it as e power minus n, which can be written as 1 by e power n. So this will be the number of fraction of nuclei undecayed after n mean lives, guys. 1 by e power n will be the case. What are they saying here? The graph showing the variation of decay rate with number of active nuclei. Decay rate is nothing but activity. Activity is given as minus dn by dt. Minus dn by dt will be what, beta? Lambda times of n. Yes or no? Or I can write it as a naught e power minus. So they are asking activity is taken on y-axis. Number of nuclei at any instant is taken on x-axis. So which graph will it follow? Y is equal to mx graph it will follow. It will be a straight line passing through origin, guys. Clear, everyone? Understood, all of you? Yes or no? So these are the questions from your nuclei chapter that I wish to explain. Clear, all of you? Tomorrow we will be doing electronic device and circuits. It's a very important topic because definitely 3 questions so will definitely be asked from that particular chapter, guys. And same situation is happening from years again. We expect the same. Again, if it is not so, then at least 2 questions so definitely will be asked. Right. So these were the questions which I thought of discussing from nuclei. Tomorrow we'll discuss questions from electronic devices and circuits. If time being, again, if possible, we will also discuss some questions from heat. Okay, clear all of you? So if there are any other doubts that you have, I would request you people to please share it so that I can give the answer of the same through WhatsApp by tomorrow, guys. Okay, so that's it from my end for today. We'll meet tomorrow and possibly the last discussion of the chapter, right? So till then, take care, everyone. Thank you all. Bye bye, all of you.